Hi, everyone, and welcome to our next set of lectures where we are going to introduce sets and set theory. Sets are really at the heart of modern mathematics, and with logic, sets form the backbone of this course. Everything we're going to do in this course is in some way going to be structured by sets and by logic. Now, what's beautiful about sets is that they are fundamentally a really, really simple idea. Definition: a set is just a collection of distinct objects, and these objects are called elements. A set is a collection of distinct elements. This is a really general kind of definition, so let's look at a few examples. Here's one. We can form a set that I'll call C. I'll just give it an arbitrary name C. The set C of all computer science majors. Every person who is a computer science major is in that set. We've just given a name to that collection of people. Here's another one. The set Z of all integers. So this one is a math set. This is the set Z of all integers. So numbers like -3 and 7 and 0 are all in this set. Whereas I gave the set of computer science majors an arbitrary name that I made up off the top of my head, the set Z is one of several special named sets. We always write it with a Z all the time to denote the set of integers. One more example. This one is a little bit more computer sciencey. Suppose I've written some cool Python function that is designed to accept some input and return some output. As you might know from a class like Introduction to Computing, your Python function doesn't necessarily work on every single possible input. If you are working on a Python function that accepts strings as inputs, then it might not work on integers, for example. So we can consider a set of all possible inputs for which your cool Python function works correctly. So this might be the set of strings, for example, if your function is guaranteed to work with all possible strings. Now, in order to write sets in a little more detail, we're going to start with a method of describing sets called roster notation. And roster notation simply means to write the elements of the set between some simple curly braces. So here's a curly brace. And I'm going to write some elements of the set of all integers Z. So this is my set Z here. Some elements of this set are things like -2, -1, 0, 1, and 2. And I'm going to put little dots here to indicate that this set continues indefinitely. This set is a finite set. It never ends, but here's another one that is finite. It has only a finite number of elements. This time it'll be a set of strings, like for my Python function. I can have just a series of strings in here. This set contains 3 strings, 1, 2, 3. It's no problem for this one to have multiple letters in it. That's fine. And then if I'm making a set of computer science majors, I can also simply write, hey, here's my, let's call it C. Here's my set C of computer science majors. And in here, I would just have name 1, name 2, and so on. So the first way that we have to write sets using roster notation just means to write them out. I write out every single element of the list, or if I have a list that has more elements that I'm able to write out, then I'll use this ... notation to indicate that the set continues. So for our first pass at sets, a set is a collection of distinct objects. No repetitions are allowed. these objects can be written in roster notation between two curly braces to indicate that that collection forms a set. Let's go into a little bit more detail about sets and their elements. We use this funny little symbol here that looks a little bit like an E to say that X is an element of a set A. So here X could be any kind of thing. It could be a number, it could be a string, it could be a person, it could be another set. X is an element of A means that X is in this collection of objects that we have called A. So let's do a quick example. Here I have a set. This set has 3 strings in it. I've called the big set A. And inside this set, I have 3 strings, letter A, letter B, and letter C. So I can pick a letter here. So B, the string B, that's inside this set. It's listed in the roster notation. And so I would say that B is an element of A. Often we also just say B is in A. On the other hand, if I picked a different letter like D, D is not in A, and we write that with this little letter like E, but we put a slash through it. Similar to writing something is not equal to something else, we say that D is not in A. Of course, we don't have to choose just letters here. So for example, the number 3 is also not an element of A. It's not there in the roster notation. We can use the idea of elements to define another concept, which is a subset. So we say that a set A is a subset of a different set B if every single element of A is also an element of set B. And we write this using this little sideways, it looks like a C, and then with a line under it. So we say that A is a subset of B written this way if every single element of A is also an element of B. So here's a few different sets. I've written out 3 different sets now. A, B, and C. These are all sets of integers. So let's take a look here and see if we can find some subset relations. So I'm going to start at the bottom here. So if I look at C, there are 2 elements here, 2 and 3 in C, and I see both of those elements in A as well. So every single element of C is also an element of A. This means that C, and I'll just highlight my symbol here, C is a subset of A. If I take a look at A, I'll notice that, hey, A has 1, 2, and 3. Those are actually all present in B as well. So again, I can say that A is a subset of B. On the other hand, if I look at A and compare it to C in the other direction, I'll notice that A has a 1, whereas C does not. This means that it's not true that A is a subset of C, and we write that using the same slash through the subset symbol. Now, when is it the case that 2 sets are subsets of each other? So what would have to have been true for A to be a subset of C as well as C to be a subset of A? In this case, I would have had to have had all the same elements in both sets. This means that C would have all the elements of A and A would have all the elements of C. And indeed, this is what it really means for 2 sets to be equal to each other. So we say that A is equal to B, so set A is equal to set B, if it's the case that A is a subset of B and, logical and B is a subset of A. And later in the course, we'll learn how to use a technique called the element method in order to prove statements like this, prove that A is equal to B as sets by showing that A is a subset of B and B is a subset of A. much like the way that logical operators allow us to form new logical propositions from old logical propositions, set operations allow us to form new sets from old sets. So let A and B be any two sets, any at all. We're going to define three different ways to combine A and B. So the first one is called the union of A and B, and it's written using this cup-shaped binary operator. The union of A and B contains every element that's either in A or B or both. So anything that's in either of these two sets goes in the union. It doesn't have to be in both, but if it is, that's okay. In contrast, the intersection of A and B contains every element that is in both A and B. So just being in one isn't enough. For the intersection, you have to be in both. Then, the set difference is our last set operator for now. A set difference, the set difference of A and B, contains every element of A which is specifically not an element of B. Everything in A which is not in B. This is a little bit abstract, but we can do a few examples to wrap our heads around things. So here's two sets. A is equal to the set of integers 1 and 2, and B has elements 2, 3, and 4. So let's compute each of these special sets. So first we're going to do the union of A and B. So the union of A and B is everything that's in either A or B or both. So when I compute the union here, I'll start with element 1. I notice that element 1 is in A. It's not in B, but that's fine. It doesn't have to be for the union, so I'll write it down. Now I move on to element 2. I observe that element 2 is in both A and B. Now remember that sets contain distinct elements. This means that I'm not going to write the element 2 twice. There are no duplicates in sets. But because it's in one or both of these sets, I'm going to write it in as well. And then I'm going to add 3 and 4. They are not in A, but they are in B, and that's enough. So that was the union. Let's also try the intersection. A intersection with B. This time, I'm looking for all the elements that are in both A and B. And when I do that, I see there's really only one of them, actually. Only 2 is in both A and B. Everything else is in only one of these two sets. And so the intersection of A and B is equal to the set with the single element 2. Then, finally, or maybe not finally, actually we'll do one more. I'll look at A set difference B. Sometimes we call this A minus B, although it's important to remember we're thinking about sets there. That's everything that's in A and not in B. In this case, the 2 is shared between A and B, but the 1 is not. So that 1 is in A, and that's the only thing that's left. And I can also do this in the other direction. So if I consider, oh, that's the same direction. If I consider B set minus A, that could give me a different answer, potentially. So here I'm looking for every element that's in B but not in A, and that lands me with the 3 and the 4. Another handy way to think about these kinds of set operations, another handy way to look at set operations is through the framework of Venn diagrams. And to look at those, I'm going to erase my exercise here. Let's take a look at a Venn diagram representation. So I have two sets A and B, and I've represented each of them as a circle. Okay. So When I think about the circle as a schematic representation of everything that's in A and a schematic representation of everything that's in B, I can then visualize the union, the intersection, and the set difference. Let's start with the union. So remember that I write the union A, B, and then my pink cup in the middle there, A union B. And if I think about the union, well, I need to be in A or B or both. Everything in A or B or both. In the context of a Venn diagram, that's just everything that's shaded. Everything that's shaded is in the union here. It's in either A or B or both. Remember that for the union, I don't have to be in both A and B. Either of them is enough, and that's why both circles and their overlap get shaded. Let's do another one. So this time, I am going to consider the intersection of A and B. So that's the upside down U. Intersection is a pretty suggestive terminology already. It sounds like overlap, for example. And here it's true. In order to be in both A and B, I need to look for the place where these two circles overlap. So this is my intersection. That's the set A and B in this context. It's not enough to be in A alone or B alone. I have to be in both A and B. Let's do another one. So for our last example, I want to consider the set difference, A set difference B. And this time, what I'm looking for everything that's in A, so that's the left circle, but not in B, which means I need to exclude the places where they overlap. So this time, my new set, the set difference of A and B, looks like this. It's the set A with a byte taken out of it because the stuff that's also in B is not emitted. So, with Venn diagrams, I can create geometric representations of sets and the results of combining sets using set operations.